At 1917 UTC on June 21, a sunspot region designated AR4473 released a flare measured at M6. 8. The strongest eruption the Sun has produced in 8 days, and it did not arrive alone. In the 24 hours surrounding that eruption, the same region fired an M2. 6. Then climbed again, then produced a partial halo coronal mass ejection associated with a flare in the M7 range. 3 significant events from a single patch of magnetic field that did not exist as a numbered region 1 week ago. NASA's Solar Dynamics Observatory captured the M6. 8 event directly, a bright filament of plasma snapping outward from the Sun's surface in a burst that released, in a matter of minutes, more energy than is consumed by the entire planet in several years. We are watching a sunspot grow in real time, and the growth is not slowing down. 1 week ago, the patch of solar surface that would become AR4473 had no number, no formal designation, and no entry in any forecast bulletin. It rotated onto the visible face of the Sun as an unremarkable cluster of magnetic disturbance, the kind that crosses the solar disk dozens of times a year and decays without producing anything beyond a background hum of small flares. Solar physicists who track these regions day to day watched this one behave differently almost immediately. It darkened, it complicated. It began producing flares that climbed in class, rather than settling into a stable pattern, and by June 21, 8 days after first appearing, it had become the only numbered region on the entire solar disk that forecasters were naming directly in a public bulletin as the source of ongoing concern. Here is what makes AR4473 different from the dozen active regions that have crossed the solar disk this year without earning a second look. Most sunspot groups stabilize within a few days of forming, settle into a simple magnetic configuration, and decay quietly off the far side of the Sun without producing anything beyond class flares. AR4473 is doing the opposite. Solar physicists classify this region as beta, a designation indicating 2 areas of opposite magnetic polarity within the same spot group, and the boundary between those polarities, the place where the magnetic field reverses direction across a span of a few thousand kilometers, is the exact geometry that produces major flares. NASA's Solar Dynamics Observatory has tracked this boundary tightening over the past several days. The region is not stabilizing, it is sharpening. The Space Weather Prediction Center, the division of NOAA responsible for forecasting solar impacts to Earth, issued a 3-day outlook on June 22, placing the probability of R1 to R2 radio blackouts at 40% for each of the following 3 days, and a 5% probability of an R3 or stronger event, specifically because of AR4473's flare potential. A 40% daily probability across 3 consecutive days is not a forecast hedge. It is a statement that the agency expects this region to keep producing measurable effects on Earth's ionosphere, and it is naming the region by number in a public bulletin, which NOAA does only when a specific source has earned that level of attention. 2 coronal mass ejections from this same general period are now converging on a single arrival window. The first, launched on June 19 before AR4473 had even grown complex enough to be numbered, is forecast to deliver what space weather analysts call a glancing blow, a partial, oblique impact rather than a direct hit, expected near 8 UTC on June 23. The second, launched June 20, is forecast to arrive roughly 26 hours later, near 10 UTC on June 24. KP index estimates for both arrivals range from 3 to 5, a band that spans quiet, unsettled, and the threshold of a minor geomagnetic storm. The agencies tracking this are clear that timing carries real uncertainty for both events. What they are not uncertain about is that 2 separate eruptions, launched a day apart from the same general region of the Sun, are now scheduled to reach Earth within roughly 26 hours of each other, and the compounding effect of back-to-back arrivals is mechanically different from either one striking alone. When a single coronal mass ejection reaches Earth, it compresses the magnetosphere, the invisible magnetic shield that surrounds the planet, and that compression is what produces a geomagnetic storm. When a second ejection arrives before the magnetosphere has fully relaxed back to its resting shape, the compression does not simply repeat. It stacks on top of a system that is still recovering from the first disturbance, and the resulting magnetic stress on the planet's field can behave in ways that a single isolated impact would not produce. This is not a hypothetical concern invented for tonight's report. It is documented physics, observed and modeled by the same agencies issuing tonight's forecast, and it is the specific reason NOAA's bulletin treats the June 23 and June 24 arrivals as a connected sequence rather than two unrelated events to be evaluated separately. We are filing this report from that window. Tonight, we walk through what AR 4473 is, what NOAA, NASA, and the International Space Weather Monitoring Network are tracking in the hours ahead, and what happens when two solar disturbances arrive close enough together that their effects on Earth's magnetic field do not fully separate. We will examine the monitoring infrastructure itself, the satellites and ground stations that allow this kind of forecast to exist at all, and we will name the specific agencies whose data we are relying on tonight so that nothing in this report rests on an unverified claim. We will look at the historical instrument record of solar storms strong enough to leave a physical mark on technology and on the ground itself, from the era before satellites to the era of GPS and the power grid, drawing on documented events separated by more than a century and a half that share a structural signature with what is unfolding above us right now. And we will close with a layer of the report that does not come from any space agency. Long before magnetometers, before radio, before anyone understood that the sun's surface could reach toward Earth across 93 million miles of empty space, multiple separate civilizations on different continents recorded specific descriptions of the sky behaving in ways that match, with a precision that deserves examination, what instruments are measuring above us tonight. We are not going to tell anyone what to make of that. We are going to put both records side by side and let the comparison speak for itself. This is what we do every night. We take the data that official channels release, often without much explanation of what it means, and we sit with it the way an analyst would. Then we go back through several thousand years of recorded human observation and ask a narrow, specific question. Has anyone described this before? And if so, in what words? Sometimes the answer is no. Tonight, the answer is more complicated than no, and it is worth sitting with why. We file a new report like this one every night on whatever the agencies are tracking that day, whether that is a solar region, a fault line, a volcanic system, or an anomaly in the ocean itself. And we run the same process every time. Verify the data first, then go looking in the historical and ancient record for anything that matches. Before we go further, we want to know where viewers are watching from tonight. Drop a location in the comments if comfortable doing so. We have people monitoring this channel from coastlines, from inland cities, from places that will see tonight's Aurora forecast and places that will not. And there is something worth noting in just how widely distributed this audience already is, watching the same sky from very different vantage points at the same hour for the same reason. The full record starts now, and it begins on the surface of the sun itself. Sunspot region AR 4473 produced its strongest flare to date at 1917 UTC on the 21st of June, 2026, an M6.8 event recorded by the GOES-19 satellite's X-ray sensor and confirmed independently by ground-based observatories monitoring the sun in real time. There is a number buried inside tonight's NOAA forecast that no general news coverage of this event has mentioned by name. Two separate coronal mass ejections, launched a day apart from the vicinity of this region, are now arriving within roughly 26 hours of each other on June 23 and June 24. We will reach why that 26-hour figure matters before this report closes. The flare arrived less than 17 hours after an earlier M2.6 eruption from the same region at 2:25 UTC that same day, and within the following day the region produced a third significant event, a flare in the M7 range accompanied by a coronal mass ejection with a partial halo signature, the visual indicator solar physicists use to describe an eruption expanding outward in a roughly symmetrical ring as seen from Earth's vantage point. 3 M-class events from a single active region inside a 36-hour window is an unusual concentration of activity, and it is the reason this region, out of the 5 numbered sunspot groups currently visible on the solar disk, is the only one named directly in NOAA's public forecast bulletins as the active source of ongoing concern. The agency responsible for that bulletin is the Space Weather Prediction Center, a division of the National Oceanic and Atmospheric Administration headquartered in Boulder, Colorado. SWPC exists for a specific reason. Solar activity does not stay contained to the sun. When the sun releases energy in the form of flares and coronal mass ejections, that energy can reach Earth and interact with the planet's magnetic field, atmosphere, and technological infrastructure. And SWPC's mandate is to monitor that activity continuously and issue public alerts, watches, and warnings calibrated to a standardized severity scale. The agency tracks 3 separate types of solar impact on independent scales. Radio blackouts are measured on an R scale from R1, a minor disruption to high-frequency radio communication, up to R5, a complete blackout affecting navigation and communication systems across an entire hemisphere of the planet for hours. Geomagnetic storms are measured on a G scale from G1, a minor disturbance, up to G5, an extreme event capable of producing widespread power grid disturbances and damage to transformers. Solar radiation storms, a separate phenomenon involving high-energy particles rather than electromagnetic radiation, are measured on an S scale. Tonight's report concerns primarily the R and G scales, because AR4473's flares are driving radio blackout risk directly, while the coronal mass ejections associated with the region's recent activity are driving geomagnetic storm risk on a slightly delayed timeline as the ejected material crosses the 93 million miles between the Sun and Earth. On June 22, SWPC's 3-day forecast placed the probability of R1 to R2, meaning minor to moderate, radio blackouts at 40% for each of the following 3 days, June 22 through June 24, with a 5% probability of an R3 or stronger event across the same window. The bulletin states explicitly that this elevated probability exists primarily due to the flare potential of region 4473. A 40% daily probability sustained across 3 consecutive days is a meaningfully different statement than a single-day spike. It means the agency's models expect this specific region to remain capable of producing measurable ionospheric disruption through the period, not as an isolated event but as an ongoing condition. Independent confirmation of AR4473's behavior comes from multiple sources outside SWPC itself. The Australian Bureau of Meteorology Space Weather Services Division, monitoring the same region from a separate hemisphere with separate instrumentation, issued its own summary on June 22, stating that of the 5 numbered sunspot regions currently on the solar disk, AR4473 is the only one showing meaningful change, specifically instability in its leading spots, the magnetically dominant portion of the sunspot group that typically drives flare production. That same bulletin notes a slow partial halo coronal mass ejection associated with the M7 flare, and states that solar radiation storm conditions at the S0 level, meaning below the threshold for an official radiation storm but still being monitored, were observed on June 21 and are expected to continue through June 24. The 2 coronal mass ejections referenced earlier deserve a closer look now that the basic picture is established. The first was launched on June 19, before AR4473 had even grown complex enough to receive its official number, and is forecast to deliver what space weather analysts call a glancing blow, a partial, oblique impact rather than a direct hit, expected near 8 UTC on June 23.
26
the second
hours,
was launched
that's
June
how long
20
it takes.
and is forecast
A new
to
day,
arrive
a
near
new
10
world,
UTC
just a
on
little
June
further
24,
away.
roughly 26 hours after the first. KP index estimates for both arrivals range from 3 to 5, a band that spans quiet, unsettled, and the threshold of a minor geomagnetic storm. SWPC's own language is careful here. The agency states plainly that timing carries considerable uncertainty for both events. That uncertainty is honest
is
and it is normal. Predicting the precise arrival time of a CME days in advance, based on a structure that is invisible to the naked eye and only inferred from coronagraph imagery, has never been an exact science. What is not uncertain is the structural fact of the sequence itself. 2 ejections, a day apart in origin, arriving roughly a day apart at Earth, both pushing the planet's magnetic field in succession, rather than in isolation. Keep that 26-hour figure in mind. We are not done with it. The monitoring infrastructure behind tonight's forecast deserves explanation because the credibility of everything that follows rests on understanding how this data is actually gathered.
Maintaining geostationary
Operational
orbit.
Environmental
This satellite is a key component of the
jointly by
global
NOAA and
communication
NASA,
network.
maintains a constellation of satellites in fixed positions relative to Earth's surface, and the current generation includes an instrument called the Solar Ultraviolet Imager, which photographs the sun continuously in wavelengths invisible to the human eye, allowing forecasters to watch flares develop in something close to real time. The X-ray sensors aboard these same satellites are what produced the official M6-8 classification for the June 21 flare. Solar flares are graded on a logarithmic scale
Warning,
running
X's
from
threshold
A through X,
exceeded,
where each
initiating
letter
protocol.
represents a tenfold increase in peak X-ray flux measured in watts per square meter, and the number following the letter refines the measurement within that order of magnitude. An M6-8 flare releases roughly 7 times the X-ray energy of an M1-0 flare, and a single X-class flare releases at least 10 times the energy of the strongest M-class event. AR4473's M6-8 places it solidly within the upper half of the M-class range, well short of X-class, but strong enough to register globally. Beyond
The
GOES,
stars are beautiful,
the monitoring network includes
but they hold
ground-based
secrets we can
magnetometers
only
stationed
dream of.
across the globe, instruments that measure tiny fluctuations in Earth's magnetic field and feed that data into the planetary K-index, the raw measurement from which the more commonly cited KP index is derived as a global average. The Solar and Heliospheric Observatory, a joint mission of NASA and the European Space Agency positioned at a gravitationally stable point between Earth and the Sun, carries a coronagraph instrument called LASCO that blocks out the Sun's
revealing the
overwhelming
Sun's
direct
corona.
light, specifically so that fainter coronal mass ejections can be photographed as they expand outward.
The cloud expands, moving ever closer to the void.
It was LASCO imagery that first confirmed the partial halo signature on the CME associated with AR4473's M7 range flare.
Two of
Further
our
out,
spacecraft
the
are
twin
now in a
stereo
stable
spacecraft,
orbit.
when
Their instruments
operational and
online
favorably
and sending
positioned,
back data.
Global
allow
constraints.
forecasters to
The green
triangulate
volume
the
rotate
CME's
beams
true
and shafts,
three-dimensional
transitioning from a flat
rather
projection
than
to a
relying on a
volumetric
single flat image, though current solar geometry limits how much additional confirmation that mission can offer for this particular sequence of events. What all of this infrastructure is built to answer is a deceptively simple question. Is the material the Sun just released heading toward Earth? And if so, when will it arrive and how hard will it hit? For AR4473's 2 pending coronal mass ejections, the answer the agencies have settled on, as of this report, is a glancing blow on June 23, followed by a more direct but still uncertain arrival on June 24. With KP estimates in the 3 to 5 range for both. That range is worth sitting with for a moment because of what it does not include. A KP of 5 marks the formal threshold of a G1 minor geomagnetic storm. The current forecast for this sequence tops out right at that threshold rather than clearly exceeding
out
it,
effect.
which means the practical effects, if the higher end of the estimate holds, would likely be confined to enhanced auroral displays visible at unusually low latitudes, minor fluctuations in high-frequency radio propagation, and negligible risk to large-scale infrastructure. We want to be precise about that because precision is the entire point of tonight's report. This is not,
Global
as of the data
constraints
available
are
when this
nominal.
report was filed, a
All
forecast for a
systems
severe
are
or
green.
extreme geomagnetic event. It is a forecast for a sustained period of elevated solar activity from a single, unusually active region, producing a sequence of effects that are individually modest but structurally unusual in their timing and concentration. That number will matter later in this report. Keep it in mind. A KP range of 3 to 5, sitting directly on the line between unsettled conditions and the formal threshold of a minor storm, for 2 separate arrivals roughly 26 hours apart. At this precise moment, as this report is filed, AR4473 remains on the visible solar disk and continues rotating toward the Sun's western limb from Earth's point of view, a detail that matters because it changes the geometry of any future eruptions from this region. Right now, the region sits close enough to direct alignment with Earth that its flares
A most
and associated
beautiful
coronal
and
mass
terrible
ejections
thing.
retain a meaningful chance of an Earth-directed component which is why the current sequence of 2 pending CME arrivals carries real forecasting weight, rather than being a footnote. As the region continues its rotation over the coming days, any new eruptions will increasingly launch from an angle that points away from Earth, reducing the geoaffected risk, even if the region's flare activity itself does not decline. This is one of the quieter mechanics of space weather forecasting. Timing matters not only in terms of when an eruption happens, but where the source region sits on the rotating face of the Sun at the moment it happens. Secondary effects from the current activity are already being logged. Radio blackouts at the R1 and R2 level, the range SWPC's forecast places at 40% daily probability through June 24, manifest as a temporary degradation or complete loss of high-frequency radio signal propagation on the sunlit side of Earth. The side facing the Sun at the moment, a flare's X-ray and extreme ultraviolet radiation strikes the upper atmosphere. This affects amateur radio operators, certain aviation and maritime communication systems that rely on HF bands for over-the-horizon contact, and in more severe cases, can degrade GPS positioning accuracy by altering the density of the ionosphere that GPS signals must travel through. None of these effects are visible to most people going about an ordinary day, which is part of why solar weather of this magnitude tends to pass without much public notice, even as it registers clearly on every instrument built to track it.
The Aurora's dance across the sky is a reminder of nature's most magnificent displays.
Public directly. With KP estimates reaching as high as 5 for the June 23 and June 24 arrivals, Aurora watchers at high latitudes, and in some cases at unusually low latitudes if the higher end of the KP range holds.
The Aurora is nature's most magnificent light show, a dance of light and energy that stretches across the night sky.
In the southern hemisphere, NOAA's Aurora forecast models, which translate KP estimates into a visibility line across the globe, currently suggest the southern hemisphere's high-latitude regions, including parts of southern New Zealand, carry some of the better prospects for visible aurora activity this week, a detail confirmed by ground observers and amateur astronomers tracking the forecast independently of the official agency bulletins. We will return to the coordinate of AR 4473's position on the solar disk before the end of tonight's briefing, because where this region sits relative to Earth, not simply what it is doing, is part of what the historical and ancient record will eventually speak to directly. 3 separate ancient traditions, on 3 different continents, recorded specific sky phenomena that modern researchers have connected to documented solar storm activity, describing the phenomena using different languages, different symbolic systems, and entirely separate calendars, yet arriving at descriptions that converge on the same physical signature: a reddening of the sky, a disturbance felt across the heavens, occurring in clusters rather than as single isolated events. The question this report will answer, by the time we reach the ancient record, is how 3 civilizations with no contact with one another arrived at strikingly similar descriptions of something none of them had the instruments to measure directly. To understand why agencies track sequences like this one as carefully as they do, it helps to understand what a geomagnetic storm actually does to the planet, mechanically, beneath the level of aurora and radiostatic that the public usually associates with space weather. Earth's magnetic field extends far beyond the planet's surface,
deflects the
forming a
solar wind,
teardrop-shaped region
shielding
of
our
space called the magnetosphere that deflects the bulk of the solar wind, the constant stream of charged particles the Sun emits even during quiet periods. When a coronal mass ejection arrives, it is not simply a gust of stronger solar wind. It is a discrete cloud of magnetized plasma, often carrying its own internal magnetic field, oriented in a specific direction, and the orientation of that field relative to Earth's own magnetic field determines how efficiently the incoming material couples with the magnetosphere. A southward-oriented field
The
within
Sun's
incoming
coronal
CME
mass
merges more
ejection has
effectively with
reached
Earth's
Earth's magnetic
northward-oriented
field
at the dayside boundary, opening a connection that allows energy and charged particles to pour into the magnetosphere far more efficiently than a northward-oriented CME would. This is why 2 CMEs of similar raw speed and density can produce wildly different geomagnetic outcomes depending on a magnetic orientation that cannot be measured directly until the material itself arrives at a solar wind monitoring spacecraft positioned roughly 1 million miles from Earth. The same spacecraft referenced in SWPC's own bulletins as the point at which true confirmation becomes possible. This uncertainty is not a flaw in the forecasting process. It is an honest acknowledgement of a genuine physical limit, and it is worth naming directly because it explains why SWPC's language throughout this period has been calibrated rather than alarmed. The agency is not withholding information. It is reporting the actual state of scientific confidence, which is that a watch, or a moderate probability forecast, represents the best available analysis until the material itself reaches instruments close enough to Earth to confirm its character. History offers a useful frame for understanding the upper bound of what this kind of activity can become, even though tonight's forecast does not currently point toward anything approaching that upper bound. In September 1859, a solar event now known as the Carrington event, named for the British astronomer Richard Carrington, who observed and documented the associated solar flare directly through a telescope, produced a geomagnetic disturbance so severe that telegraph systems across Europe and North America failed, in some documented cases continuing to transmit signals for hours even after operators had disconnected their batteries, powered entirely by the electrical currents the storm induced directly into the telegraph wires themselves. Aurora was reported as far south as the Caribbean. Contemporary newspaper accounts describe skies bright enough at high latitudes that people could read a newspaper outdoors at night by the glow alone. Modern researchers, working backward from ice core records that preserve a chemical signature of energetic particle bombardment, estimate the Carrington event was at minimum an extreme G5 class storm, and some analyses suggest it may have exceeded the upper bound of the modern G scale entirely. A second event, in March 1989, produced a geomagnetic storm that the Hydro-Québec power utility in Canada experienced directly when induced currents tripped protective relays across its transmission network, triggering a cascading failure that left 6 million people without power for approximately 9 hours. That event registered as a G5 storm and remains one of the most thoroughly documented examples of a geomagnetic disturbance translating directly into infrastructure failure on a continental power grid. We are not telling you tonight's sequence resembles either of these events in scale. The KP 3 to 5 range projected for the June 23 and June 24 arrivals sits orders of magnitude below the disturbance levels associated with Carrington or the Quebec blackout. We are telling you this history because it establishes the structural mechanism, the same mechanism currently in play at a far smaller scale, and because the historical record of solar storms shows a consistent pattern worth naming. The most severe events in the documented era have tended to arrive not as a single, isolated eruption, but as a sequence, one disturbance following closely behind another, each one priming the magnetosphere for what comes next. That pattern, a sequence rather than a single strike, is the specific structural feature connecting tonight's forecast to both the historical instrument record we are about to walk through and the ancient record waiting at the end of this report. A third agency deserves specific mention here, distinct from NOAA and the Australian Bureau of Meteorology already discussed. NASA's Goddard Space Flight Center, through its Heliophysics Science Division, maintains the scientific instrumentation aboard the Solar Dynamics Observatory and coordinates the broader research effort to understand solar behavior at a level of detail that goes beyond the operational forecasting NOAA performs. Where NOAA's Space Weather Prediction Center exists to issue actionable public warnings calibrated to immediate risk, NASA's heliophysics research exists to understand the underlying physics in enough depth that forecasting itself can improve over time. The two missions are complementary rather than redundant, and the SDO imagery referenced earlier in this report, the footage capturing AR-4473's M6. 8 FLARE directly is a NASA-operated instrument feeding data that NOAA then incorporates into its own operational forecasts. When multiple agencies with different mandates and different instrumentation independently arrive at the same basic picture, naming the same region, tracking the same flare classifications, and converging on the same general forecast window, that convergence is itself a form of verification that matters. It is worth being direct about what official channels have and have not said regarding AR-4473's longer-term trajectory. No agency tracking this region has issued any statement suggesting an X-class flare is imminent or even likely in the near term, though SWPC's own bulletin does note a 5% probability of an R3 or stronger radio blackout, which would require at minimum an M5 class flare and likely something stronger across the June 22 to June 24 window. A 5% probability is not nothing, and it is also not a majority likelihood. The honest position, the one every agency cited in this report has taken, is that AR4473 remains the region to watch on the solar disk, that its magnetic complexity has increased rather than decreased over the past several days, and that the coming 72 hours represent the most active monitoring window for this specific region since it first received a number. We have now covered what the instruments are measuring, what the agencies are forecasting, and what the underlying physics of a coronal mass ejection arrival actually involves. Before we turn to the historical instrument record and then to the ancient record that closes this report, there is one more piece of live data worth placing on the record, precisely because it has not appeared in any general coverage of this event that we have reviewed. The spacing between the two pending CME arrivals, the 26-hour figure mentioned earlier in this report, is close enough to the rotational period most commonly associated with recurring solar activity from a single active longitude that some space weather researchers flag windows like this one for closer attention, not because the spacing itself is unusual in isolation, but because back-to-back arrivals compress the magnetosphere's recovery time in a way single events do not. We are filing that detail now, plainly, without speculation beyond what the mechanism itself supports. The historical record, which we turn to next, shows exactly this kind of compressed sequence appearing again and again whenever instruments have been sensitive enough to catch it. The KP index, referenced repeatedly throughout tonight's forecast, deserves a fuller explanation than the number itself usually receives in casual coverage, because understanding how it is built clarifies exactly what kind of claim a forecast of KP 3 to 5 is actually making. The index is derived from data collected at 13 geomagnetic observatories distributed across the globe, each one operating a magnetometer that continuously measures the strength and direction of the local magnetic field. These observatories are deliberately spread across a range of latitudes and longitudes specifically so that the resulting index reflects a planetary average rather than a single region's experience. A magnetometer in northern Scandinavia will register a geomagnetic disturbance differently than one near the equator, both because of the underlying physics of how charged particles funnel toward the poles along Earth's magnetic field lines, and because auroral activity itself concentrates at high latitudes. The KP index compensates for this by standardizing each station's reading against its own typical baseline before averaging across the network, producing a single global number on a scale from 0 to 9 that updates every 3 hours. A KP of 0 to 2 describes quiet conditions, the normal background state of Earth's magnetic field on an undisturbed day. A KP of 3 to 4 describes unsettled to active conditions, noticeable to the instruments but well short of storm classification. A KP of 5 is the formal threshold for a G1, minor geomagnetic storm, and each subsequent integer up to 9 corresponds to increasingly severe G-scale classifications, with KP9 corresponding to a G5 extreme storm. The same classification reached during the 1989 Quebec event and almost certainly exceeded during the 1859 Carrington event before the KP scale itself existed in its modern form. Tonight's forecast, projecting a range of 3 to 5 for the pending CME arrivals, places the expected disturbance right at the boundary between unsettled conditions and the minimum formal storm threshold, which is precisely why SWPC's own language throughout this period has used calibrated, conditional phrasing rather than issuing an outright storm warning at a higher level. It is worth understanding why a 3-hour update cadence exists at all, rather than continuous real-time reporting. The underlying magnetometer data is in fact continuous, collected and transmitted constantly from each of the 13 stations, but the KP index itself is a processed, averaged product. And the 3-hour window reflects a balance between responsiveness and the kind of noise reduction that prevents short-lived, localized fluctuations from producing a misleadingly volatile global number. Forecasters working the floor at SWPC have access to the raw, continuous magnetometer feeds, in addition to the processed KP index, which is why agency bulletins are sometimes able to describe developing conditions in finer detail than the headline KP number alone would suggest, noting, for instance, a brief southward dip in the interplanetary magnetic field's BZ component that recovered before driving significant activity, a level of granularity that comes directly from continuous monitoring rather than the 3-hour aggregate. This same monitoring network, incidentally, is what allows researchers studying historical solar storms predating the satellite era to reconstruct what happened with genuine scientific confidence rather than relying solely on contemporary written accounts. Ice cores extracted from Greenland and Antarctica preserve a chemical signature, specifically elevated concentrations of certain nitrate and beryllium isotopes, that forms when energetic particles from a major solar event interact with Earth's atmosphere and eventually settle into accumulating ice layers that can be dated with precision by counting annual deposition bands, much like tree rings. This is the method that allows modern scientists to look at the Carrington event of 1859, more than a century before any magnetometer network existed in its current form, and assign it a confident estimate of extreme severity based on physical evidence preserved in polar ice rather than written testimony alone. The written testimony and the ice core evidence agree with each other, which is itself a notable form of cross-verification between an instrumental record and a human one, a pairing of evidence types we will return to directly when this report reaches its ancient record section. The agency's own forecasters have been candid, in public statements surrounding events of this kind, that confidence in any CME's geomagnetic storm potential remains limited until the material arrives at instruments positioned roughly 1 million miles from Earth, close enough to measure the cloud's true magnetic orientation and density before it reaches the planet itself. This is not a failure of the forecasting science. It reflects an honest limit. The magnetic orientation of an Earth-directed coronal mass ejection, the single most important variable in determining how strongly it will couple with Earth's own magnetic field, simply cannot be measured remotely with full confidence from images alone. It can only be inferred, refined as more data accumulates, and finally confirmed in the narrow window between a monitoring spacecraft's detection and the material's arrival at Earth itself, typically somewhere between 30 and 60 minutes of advance warning once true confirmation becomes possible. Beyond the official agency network, a parallel layer of observation exists in the community of amateur and professional solar observers who track active regions independently and often publish detailed analysis. Faster than any government bulletin can be drafted and cleared for release, solar physicist communications shared publicly in the hours following the M6. 8 Flare described AR 4473 as the undisputed source of the period's activity, noting that the region fired every significant flare during the 24-hour window in question, and flagged its beta-gamma magnetic complexity as the specific structural feature that places it under continued close watch. This characterization, beta-gamma, refers to a magnetic configuration even more complex than the simple beta classification mentioned earlier in this report, indicating multiple areas of mixed magnetic polarity within a single sunspot group rather than a cleaner two-pole structure, and beta-gamma regions are statistically associated with a meaningfully higher likelihood of producing major flares than simpler magnetic configurations. Ground-based hydrogen alpha imaging, a photographic technique that filters sunlight to isolate a specific wavelength emitted by hydrogen in the sun's lower atmosphere, has captured AR 4473 directly from observatories on the ground, showing filament structures and the kind of active region detail that complements the X-ray and extreme ultraviolet imagery captured by orbital instruments. Imagery shared from ground observers in Arizona on June 21 documented active regions, filaments, and prominences across the solar disk, with AR 4473 clearly labeled among the most prominent features visible at the time, a visual confirmation that exists independently of any single satellite or government agency. The radio sun, a separate measurement tracking the sun's emission at the 7 centimeter radio wavelength, registered at 128 solar flux units as of June 22, a figure that serves space weather researchers as a general proxy for overall solar activity levels, distinct from any single flare or region but useful for placing the current period in a broader context of solar cycle behavior. The current solar cycle, the roughly 11-year pattern of rising and falling activity that the Sun has followed for as long as continuous sunspot records have been kept, appears to be in a period where individual active regions like AR 4473 can still produce significant isolated activity even as the broader cycle trends toward its declining phase, a nuance that matters because it explains why a single region's behavior can still command this level of attention even outside of solar maximum. Spotless days, a separate metric tracking how many days in a given year the Sun's visible disk shows no sunspots at all, currently sit at 0 for the ongoing stretch as of this report, and the cumulative count for 2026 stands at only 3 spotless days for the entire year so far, a low figure consistent with a Sun that remains active enough to reliably produce regions like AR 4473 with some regularity. This stands in sharp contrast to deep solar minimum years, when spotless days can account for well over half of an entire calendar year and active regions of any real complexity become comparatively rare. The current environment is one where the Sun is reliably active, where new regions form, complicate, and occasionally produce events worth a dedicated forecast bulletin, and AR 4473 is simply the latest and currently most significant example of that ongoing pattern. None of this changes the operational forecast already detailed in this report. It does, however, place AR 4473 in a wider context, a moderately active phase of the solar cycle, a Sun producing sunspots reliably rather than sparsely, and a specific region that has, within the span of about a week, gone from an unremarkable patch of magnetic disturbance to the singular focus of multiple independent monitoring agencies across at least 3 continents. That is the live picture as this report is filed. Satellite operators are among the most attentive audiences for a forecast of this kind, and it is worth detailing exactly why, because the relationship between solar activity and satellite risk is more specific than the general public discussion of space weather usually conveys. Increased X-ray and extreme ultraviolet output from a flaring active region heats and expands Earth's upper atmosphere, the thermosphere, causing it to puff outward to a degree that increases atmospheric drag on satellites in low Earth orbit. This is a measurable, trackable effect, and tonight's data shows it directly. The Thermosphere Climate Index, a metric tracking how much energy the upper atmosphere is radiating away as a proxy for its overall thermal state, registered at 14.75 times 10 to the 10th watts as of this report, a reading well above the coldest recorded minimum, but still a relatively neutral value compared to the index's documented extremes, which range from a cold minimum near 2.5 inches February 2009 to a hot maximum exceeding 49 inches, October 1957. The current reading reflects a thermosphere in a moderately energized but not extreme state, consistent with a broader picture of an active but not extreme phase of the solar cycle. Beyond atmospheric drag, geomagnetic storms can induce small electrical currents directly in satellite electronics and in long conductors on the ground, including power transmission lines and pipelines, through a process called geomagnetically induced current. The severity of this effect scales steeply with storm intensity, which is why the 1989 Quebec event at G5 caused a continental power failure, while a G1 or low G2 event, the range associated with tonight's forecast if the higher end of the KP 3 to 5 estimate holds, typically produces effects too small to register as anything beyond a data point in a utility company's monitoring logs. Grid operators in regions with documented sensitivity to geomagnetic disturbance, including parts of the northern United States, Canada, and Scandinavia, maintain their own internal monitoring thresholds and have access to the same NOAA forecasts referenced throughout this report, allowing for operational adjustments well before any disturbance reaches a level capable of causing actual equipment damage. GPS and other satellite navigation systems represent a third category of infrastructure sensitivity worth naming specifically. These systems depend on extremely precise timing signals traveling from satellites to ground receivers, and the signal's travel time is affected by the density and structure of the ionosphere it passes through. A solar flare's burst of X-ray and extreme ultraviolet radiation can rapidly increase ionospheric density on the sunlit side of Earth, introducing what engineers call ranging error, a small but measurable distortion in the calculated position, a GPS receiver reports. For most consumer applications, checking a map or tracking a delivery, this distortion is invisible. For applications requiring centimeter-level precision, including certain forms of precision agriculture, surveying, and aviation approach systems, even a brief period of elevated ionospheric disturbance can require operators to flag GPS-derived data as temporarily less reliable until conditions normalize. These are the specific, concrete channels through which a sunspot 93 million miles away translates into measurable effects on technology built and operated entirely on Earth's surface and in its immediate orbital environment. None of them, based on the data available as this report is filed, are forecast to reach a severity that would be obvious to someone not specifically monitoring for it. That is, in a sense, the entire point of tonight's report. The gap between what the instruments are recording in exacting and continuously updated detail and what reaches general public awareness is often wide enough that an event drawing this much dedicated agency attention can pass beneath the notice of nearly everyone it is quietly affecting. There is one more specific detail worth placing on the record before we move forward, because it speaks directly to the coordinate this report referenced earlier. AR 4473's position on the solar disk, as of June 22, sits close enough to the Sun-Earth line that any new eruption from the region over approximately the next 4 to 5 days retains a non-trivial chance of an Earth-directed component. After that window, as the Sun's roughly 27-day rotation carries the region toward and past the western limb, the geometry shifts decisively away from Earth, and AR 4473's remaining activity, however intense, would launch its effects into space on a trajectory that does not intersect our planet at all. We are inside that window right now. There is a name in the ancient record that, when we reach it, will describe a sky disturbance recurring in exactly the kind of clustered sequence this report has been tracking all evening. We are not there yet. Space weather monitoring is, by necessity, an international effort, and it is worth naming the structure of that cooperation directly because it is part of what gives tonight's forecast its credibility. No single nation's space agency monitors the entire sun continuously from every angle, and no single ground-based observatory network covers every longitude on Earth equally well. The practical solution the international scientific community settled on decades ago is a standing cooperative arrangement in which observatories, satellites, and forecasting centers across multiple countries share data in near real time, cross-checking each other's findings and filling in coverage gaps created by time zones, weather, and instrument downtime. NOAA Space Weather Prediction Center in the United States, the Australian Bureau of Meteorology's Space Weather Services, the United Kingdom's Met Office Space Weather Operations Center, and equivalent agencies in Japan, China, and across the European Space Agency's member states all participate in this loose but functional network and a forecast that achieves consensus across several of these independent centers, as tonight's AR 4473 forecast carries a different evidentiary weight than a single agency's internal assessment. This matters specifically because space weather forecasting, unlike terrestrial weather forecasting, deals with a source object, the sun, that cannot be directly sampled the way a meteorologist can fly a weather balloon into a storm system. Everything known about AR 4473's internal magnetic structure is inferred from remote sensing, X-ray imagery, magnetic field mapping derived from the Zeeman splitting of spectral lines, and statistical comparison against thousands of previously observed active regions whose later behavior is already documented. When multiple independent agencies, using different instruments and different analytical pipelines, converge on the same basic assessment, the convergence itself functions as a form of validation that single agency forecasting cannot provide on its own. It is also useful to place AR 4473 against the backdrop of comparable activity earlier in this same solar cycle, both to calibrate expectations, and because the comparison illuminates something about how frequently regions of this general character actually appear. Earlier in the year, a separate active region designated AR4455 produced a sequence of 3 major flares within roughly 24 hours, including an X1. Zero event, the strongest classification on the standard scale, accompanied by multiple Earth-directed coronal mass ejections that prompted a G3, strong, geomagnetic storm watch for a 2-day window. That event represented a more severe forecast than tonight's AR4473 sequence, both in terms of the peak flare classification reached and the storm category placed on watch. A separate region, AR4465, produced a filament eruption and an associated CME forecast to deliver a glancing blow to Earth's magnetosphere, a forecast structurally similar in character to one of the 2 CME arrivals currently pending from AR4473, though originating from a different region entirely. These comparisons are offered here for calibration, not equivalence. AR4473 has not, as of this report, produced an X-class flare, and the KP 3 to 5 range forecast for its pending CME arrivals sits below the G3 watch issued during the AR4455 sequence. What AR4473 shares with both of those earlier episodes is the basic structural pattern this report keeps returning to. A single region, growing in complexity over a matter of days, producing a cluster of major flares in close succession, with coronal mass ejection arrivals following close enough together that their combined effect on Earth's magnetosphere cannot be evaluated as 2 fully separate, independent events. A separate and unrelated thread of solar monitoring deserves brief mention here for completeness, distinct from the active region activity this report has focused on. NASA's Mars rover missions carry radiation sensors as part of their scientific payload, instruments originally intended to characterize the radiation environment a future human mission to Mars would need to survive, and these same sensors incidentally function as a second, independent vantage point on solar particle events, observing the sun's output from a location tens of millions of miles from Earth's own monitoring network. While no significant correlated detection from the Mars-based instruments has been reported in connection with AR4473's current activity, the existence of this entirely separate observational vantage point, monitoring the same star from a different point in space, reflects how thoroughly distributed solar monitoring infrastructure has become across the solar system, not merely across this planet. The agency released a second figure alongside its headline forecast that most general coverage of this event has not cited directly. Buried within the same June 22 bulletin that placed R1 to R2 radio blackout probability at 40% daily, SWPC also noted that solar wind speeds, which had been running in a slow background regime between 360 and 420 kilometers per second through the period, are expected to become enhanced beginning around June 24 due to the influence of several patchy coronal holes rotating into a geo-effective position entirely separate from the AR4473 flare activity and CME arrivals already discussed. A coronal hole is a region where the sun's magnetic field opens directly into space rather than looping back to the surface, allowing a faster, more direct stream of solar wind to escape continuously, distinct in character from the discrete, eruptive nature of a coronal mass ejection. This means the June 24 window, already carrying the second of the 2 pending CME arrivals, will potentially also see the onset of an enhanced, high-speed solar wind stream from an unrelated source, layering a third distinct disturbance mechanism onto the same 48-hour period. Most general coverage of this event has reported the flare and the 2 CMEs. Almost none has reported the coronal hole stream arriving in the same window. We are placing it on the record now. What this means practically is that June 24 carries the highest concentration of independent disturbance mechanisms of any day in the current forecast window, the second of the 2 pending CME arrivals, the onset of an enhanced solar wind stream from coronal holes unrelated to AR4473, and the continued elevated flare potential from AR4473 itself, which SWPC's 3-day outlook still places at 40% for R1 to R2 radio blackouts through that date specifically. 3 separate mechanisms, converging on a single 48-hour window, each individually modest in projected severity, together representing the most complex single day of space weather this monitoring period has produced. It is worth being precise about what this convergence does and does not mean. It does not mean these three mechanisms will necessarily combine to produce an outcome more severe than the sum of their individually modest forecasts. Geomagnetic storm intensity is not simply additive in a plain arithmetic sense. The relationship between multiple simultaneous solar wind disturbances and the resulting magnetospheric response involves the same orientation-dependent coupling physics described earlier in this report, and a coronal hole stream arriving with an unfavorable magnetic orientation relative to Earth's field could in principle do very little, even while a CME arriving in the same window does more. What the convergence does mean, with confidence, is that June 24 represents the single highest information day in this entire forecast window, the day on which the largest number of independently monitored solar phenomena are scheduled to interact with Earth's magnetic environment at once, and it is the day every agency referenced in this report is treating as the primary focus of continued monitoring. We have now walked through the full live picture, the region itself, its flares, its magnetic complexity, the monitoring infrastructure built to track it across multiple nations and multiple types of instrument, the two pending coronal mass ejections, and the coronal hole stream now layering onto the same window, and the specific, honest uncertainty that remains in every agency's forecast language until confirmation arrives in the narrow window before Earth impact itself. One further dimension of tonight's data deserves attention before this report turns to history. The question of why a region like AR 4473 develops the specific magnetic complexity it has, rather than remaining a simple, stable sunspot group for its entire visible transit across the solar disk. Sunspots form when concentrated bundles of magnetic field, generated deep within the sun's convective interior, rise buoyantly to the surface and break through, creating a region where the magnetic field is strong enough to suppress the convective motion that normally carries heat to the surface, producing the characteristically darker, cooler appearance that gives a sunspot its name relative to the surrounding photosphere. A simple sunspot group typically contains two main spots of opposite magnetic polarity, connected by a relatively smooth, well-organized magnetic field, the alpha or simple beta configuration mentioned earlier in this report. AR 4473's progression toward a beta-gamma classification indicates that additional magnetic flux has emerged within the same region after its initial formation, flux that is not cleanly organized relative to the original spot pair, creating the kind of magnetically stressed, twisted configuration that solar physicists have long associated with elevated flare risk. This process, continued flux emergence after a region's initial appearance, is precisely what ground-based and satellite observers have been documenting in AR 4473 over the past several days, and it is the underlying physical reason the region has been escalating rather than stabilizing. A region that simply emerges, produces a handful of flares, and then begins to decay typically shows declining magnetic complexity over time as the original flux dissipates. A region that continues receiving fresh magnetic flux from below the surface can instead show increasing complexity and increasing flare potential for as long as that fresh flux continues to emerge. Whether AR 4473 will continue this pattern, stabilize, or begin to decay is precisely the open question. Every agency cited in this report is monitoring continuously, and it is the reason the forecast language throughout this period has remained calibrated to ongoing observation rather than a single fixed prediction. We have covered in full what AR 4473 is, what NOAA, NASA, the Australian Bureau of Meteorology, and the broader International Space Weather Monitoring Network are tracking through this window, the underlying physics connecting a sunspot's magnetic structure to the forecasts built around it, and the specific, honest uncertainty that remains a permanent feature of this kind of forecasting rather than a gap in the science. The live picture, as this report is filed, is one of sustained, elevated activity from a single growing region, two pending coronal mass ejection arrivals, an additional coronal hole stream layering onto the same window, and a monitoring apparatus spanning multiple continents and multiple types of instrument, all converging on the same conclusion. Watch this region and watch this window closely. The modern instrument record did not begin with satellites or with GOES X-ray sensors. It began more than a century and a half earlier, with nothing more sophisticated than human observers stationed at telescopes, simple compass needles tracking deflection in Earth's magnetic field by hand, and the earliest telegraph lines strung across continents, wires that became, almost by accident, among the first instruments ever to register a solar storm's direct electrical signature. That record, built by people with none of tonight's satellites and none of tonight's automated forecasting, is where we turn next. The Carrington event of September 1859 remains the benchmark against which every subsequent solar storm is measured, and the documentation surrounding it is unusually rich for an event that predates modern instrumentation by more than a century. On the 1st of September 1859, the British astronomer Richard Carrington was observing the sun through a telescope at his private observatory in Redhill, England, projecting the solar image onto a screen as was his routine practice for tracking sunspot groups, when he witnessed two brilliant points of white light erupt suddenly from within a large sunspot group, intensify for approximately 5 minutes, then fade and disappear. Carrington had, without realizing the full significance at the time, become the first person in recorded history to directly observe and document a solar flare. He noted the time precisely and reported the observation to the Royal Astronomical Society. 17 to 18 hours later, a geomagnetic storm of extraordinary intensity struck Earth. Telegraph operators across Europe and North America reported their equipment behaving erratically, sparking, and in several well-documented cases, continuing to send and receive signals for a period of time, even after operators had deliberately disconnected the batteries powering their lines. The induced current from the geomagnetic disturbance itself, sufficient to operate the telegraph key. Aurora displays were reported as far south as the Caribbean and Hawaii, locations that under normal conditions never see auroral activity of any kind, and contemporary accounts from multiple cities describe night skies bright enough that people read newspapers outdoors by the light alone. Modern researchers, working from ice core samples extracted from Greenland that preserve a chemical signature of the energetic particle bombardment associated with extreme solar events, have confirmed the Carrington event's severity independently of the written historical record, and the two lines of evidence, testimony and physical trace, agree closely. Some modern estimates, based on this ice core evidence, place the 1,859 storm's intensity at a level that would, if it struck the modern electrical grid directly, cause damage estimated by various infrastructure studies to run into the hundreds of billions of dollars and require months rather than hours to fully repair, owing to the much greater dependence of contemporary society on continuously functioning electrical infrastructure compared to the largely telegraph-based world of 1,859. There is a name in the historical record specifically associated with this event that deserves mention. Carrington was not alone in observing the precipitating flare. An amateur astronomer named Richard Hodgson, observing independently from a separate location in England, recorded nearly identical observations of the same brightening within the sunspot group at essentially the same time, an independent corroboration that gave the scientific community of the period confidence that what Carrington described was a real solar phenomenon rather than an instrumental artifact or observational error. The same kind of multi-observer corroboration that gives tonight's AR 4473 forecast its credibility across multiple independent national agencies. A second, less famous but thoroughly documented event occurred in March 1989, when a series of solar flares and an associated coronal mass ejection produced a geomagnetic storm that struck Earth on March 13. In the Canadian province of Quebec, the Hydro-Québec power utilities transmission network experienced induced geomagnetic currents strong enough to trip protective relays, triggering a cascading failure across the system. The blackout left approximately 6 million people without electrical power for roughly 9 hours in the middle of a Canadian winter night, a documented infrastructure failure with a direct, traceable, single-cause chain running from a flare on the sun's surface to a continental power grid going dark. The failure sequence itself is documented in detail by Hydro-Québec's own post-event engineering analysis. Induced currents flowing through the network's long transmission lines, intended to carry alternating current at a stable frequency, introduced a direct current-like component that saturated transformer cores across the system within a span of roughly 90 seconds, triggering protective relays designed to isolate equipment from dangerous overloads, and the resulting cascade of automatic disconnections brought down the entire La Grande complex transmission system before operators could intervene manually. The event also produced vivid aurora displays as far south as Texas and Florida and disrupted satellite operations, including a documented temporary loss of attitude control on at least one orbiting spacecraft, an early warning of the same satellite vulnerability that would reappear decades later in a different form. That number will matter later in this report. 6 million people, 9 hours, a single traceable cause. A third, more recent example offers a useful contrast in scale and consequence. In February 2022, a relatively modest geomagnetic disturbance, far below the severity of either Carrington or the Quebec event, struck Earth shortly after SpaceX had launched a batch of 49 Starlink satellites into a low deployment orbit. The increased atmospheric drag produced by the storm's heating of the upper atmosphere was sufficient to prevent up to 40 of those satellites from reaching a stable operational orbit, and the satellites instead re-entered the atmosphere and burned up within days, a loss the company itself confirmed publicly and attributed directly to the geomagnetic disturbance's effect on atmospheric density at the satellite's low deployment altitude. This event is documented directly by the satellite operator itself and stands as one of the clearest modern illustrations of how even a comparatively minor geomagnetic disturbance, well below the kP threshold typically associated with infrastructure concern, can produce a concrete, costly, and entirely real-world consequence when it intersects with a vulnerable piece of modern technology at precisely the wrong moment in its operational life. The parallel to tonight's forecast is direct. This report is not suggesting tonight's sequence resembles either of these events in scale. The kP 3 to 5 range projected for AR4473's pending CME arrivals sits in a similar moderate band, not extreme by any historical measure, and yet the 2022 Starlink event demonstrates clearly that moderate does not mean inconsequential when the timing intersects with the right piece of infrastructure. A fourth historical thread, distinct from the documented instrumental events above, comes from the longer published record of major geomagnetic storms compiled by researchers studying the full pre-satellite era using a combination of telegraph records, magnetometer readings from the small number of observatories that existed in the late 19th and early 20th centuries, and newspaper accounts of unusual aurora activity. This compiled record shows a consistent structural pattern across multiple decades and multiple independent events. Severe geomagnetic disturbances rarely arrive as a single, isolated strike. They tend to cluster, one significant disturbance following closely behind another within a span of days, as a single active region or a closely spaced sequence of active regions on the rotating solar disk produces multiple eruptions before finally stabilizing or decaying. The May 1921 storm, among the most severe on record after Carrington, struck on the 15th of May 1921 and is documented through newspaper accounts and the telegraph and early telephone network disruptions it caused across the United States, including a well-documented fire at a railway signal tower in New York Central Station caused directly by induced current overheating equipment and widespread disruption to transatlantic telegraph cable communication. This storm followed a period of several days of elevated solar activity rather than arising from a single isolated event, a pattern the historical record shows again in the lead-up to the 1989 Quebec storm, which followed several days of escalating flare activity from the source region before the disturbance that actually struck the grid. This is the connecting observation worth sitting with directly. In every one of these four historical cases, from 1859 through 1989 to 2022, the severity or consequence of the event traced back not to a single flare in isolation, but to a specific combination of timing, sequence, and what happened to be vulnerable on Earth at the moment the disturbance arrived. Carrington's severity came from the raw magnitude of a single extraordinary event. Quebec's consequence came from a vulnerable grid intersecting with a strong but not historically extreme storm. The 2022 Starlink loss came from newly deployed, fragile satellites intersecting with a comparatively modest disturbance. The pattern across all of them is that the human and technological context the storms arrives into matters as much as the storm's raw intensity, and that clustering, sequence, and timing recur again and again as the decisive factor. By the time we reach the final section of tonight's report, the reason this same clustering pattern appears in records written thousands of years before telegraph wires or satellites existed will be considerably clearer. Hold that thought. The ancient record is about to make tonight's data considerably more interesting than a single number on a forecast bulletin. The pattern in the modern instrument record is clear and consistent across more than a century and a half of documentation, but we do not stop at the modern record. There is an older layer, tablets, manuscripts, oral traditions, documented predictions that logged events matching this signature long before our instruments existed to confirm them. That layer is what comes next. The oldest systematic written record of sky watching tied directly to political and agricultural consequence comes from Babylon, and it survives today on clay tablets that have been studied, translated, and cross-referenced by historians of science for well over a century. The tradition is known collectively as the Enuma Anu Enlil, a series title taken from the opening words of the compilation, which translates roughly to When the Gods Anu and Enlil, and the series consists of approximately 70 tablets recording astronomical and meteorological omens compiled over a span of centuries, with the surviving copies dating primarily from the first millennium BCE, though the tradition itself reaches back considerably earlier. These tablets were maintained by a professional class of scribes attached to the royal court, men whose specific job was to observe the sky every night, record what they saw in a standardized cuneiform format, and report directly to the king any phenomenon that the established omen tradition associated with political, military, or agricultural consequence. This was not folk astrology practiced by isolated mystics. It was a state-funded, methodical, centuries-long observational program, arguably the longest continuously maintained sky observation project in human history, predating any other comparable tradition by a significant margin. The specific category of Enuma Anu Enlil omens relevant to tonight's report concerns unusual reddening or disturbance of the sky not attributable to ordinary sunset, sunrise, or weather, described in the tablets using language that scholars studying the corpus, including the historian Francesca Rochberg in her detailed academic study of Babylonian celestial science, have translated as referring to the sky appearing to burn, redden, or take on a blood-like coloration outside of expected conditions, frequently associated in the omen literature with disturbance reaching toward or affecting the heavens broadly, rather than a single localized point. Crucially, and this is the detail that matters most for tonight's comparison, the surviving tablets do not describe these reddening events as isolated, one-time occurrences. The omen literature explicitly catalogs them in clusters, noting when a reddening recurs within a short span of nights, treating a recurrence within the same lunar cycle as a more significant and more carefully recorded omen than a single isolated occurrence. The scribes who compiled this record had no concept of a coronal mass ejection, no understanding that the sun itself could be the source of the disturbance they were cataloging, and certainly no instrument capable of measuring a magnetic field. What they had was centuries of patient, disciplined, nightly observation and a recording system precise enough to notice and specifically flag the difference between a single sky disturbance and a clustered sequence of them. This distinction between an isolated event and a clustered sequence is precisely the structural feature this report has been tracking since the briefing section. When we first noted that the two coronal mass ejections associated with AR 4473 are arriving within roughly 26 hours of each other, rather than as a single isolated impact. The Babylonian scribes, observing the sky with the naked eye and recording what they saw using an omen classification system built over centuries, arrived independently at the same basic insight. Modern space weather forecasters have arrived at using satellites and magnetometers. A single disturbance and a closely clustered pair of disturbances are not the same category of event, and the second deserves to be logged and weighted differently than the first. Multiple tablets within the Enuma Anu Enlil corpus reinforce this same pattern. Tablet sequences associated with what scholars catalog as the Omen series concerning solar and lunar disturbance describe instances where a reddening or disturbance is observed, followed within a small number of nights by a second related disturbance, and the Omen interpretation attached to this specific clustered pattern differs from the interpretation attached to either event considered alone. The scribe Balassi, whose individual astrological reports to the Assyrian king survive among the broader corpus held today in the British Museum's collection and documented extensively in Herman. Hunger's published compilation of astrological reports to the Assyrian kings specifically notes the practice of waiting to see whether an observed celestial disturbance would recur before finalizing the omen's interpretation, a methodological habit that mirrors, with a precision worth sitting with, the modern forecaster's own practice of treating a first CME arrival as context for evaluating the significance of a second one arriving close behind it. What the Babylonian scribes who recorded this material understood themselves to be documenting was not, by their own framework, a physical phenomenon originating from a star 93 million miles away. They understood themselves to be reading a message, a sign communicated through the visible sky that carried implications for the king, the harvest, or the stability of the realm, and the entire elaborate cataloging system existed to interpret that message correctly. The physical mechanism was invisible to them entirely. What was not invisible, and what they recorded with a precision that modern translators can still verify against the surviving tablets today, was the pattern itself. Disturbance, recurrence, and the specific significance of disturbances arriving close together rather than in isolation. A second tradition, geographically and culturally distinct from Babylon, though emerging from the same broader region of the ancient Near East, and likely composed within a few centuries of the later Enuma Anu Enlil tablets, comes from the Hebrew Bible, specifically the Book of Joel, a short prophetic text whose precise date of composition remains debated among biblical scholars, but which is generally placed somewhere in the post-exilic period, likely sometime in the 4th or 5th century BCE based on internal linguistic and historical evidence. The relevant passage, found in the 2nd chapter, describes a coming day using specific celestial imagery, the sun turning to darkness and the moon to blood, occurring before what the text calls a great and terrible day, with the description embedded in a broader prophetic passage concerned with judgment, repentance, and the pouring out of a spirit upon all people. Biblical scholars studying this passage have long noted that the specific pairing of imagery, a darkened sun alongside a blood-colored moon, does not in plain terms describe an ordinary solar or lunar eclipse, since the two phenomena described together, sun darkening and moon reddening, do not occur simultaneously under standard eclipse mechanics. A solar eclipse and a lunar eclipse cannot happen on the same calendar day, by definition, since one requires a new moon and the other a full moon. This mismatch has led generations of scholars to treat the passage as either purely symbolic, a poetic invocation of cosmic upheaval without literal observational basis, or, in a smaller but persistent strand of scholarship, as possibly describing a genuine atmospheric or celestial disturbance witnessed by the text's author or the broader community from which the tradition emerged, a disturbance capable of producing both a dimming of the sun's apparent brightness and a reddening of the moon's appearance through some shared atmospheric mechanism rather than through the separate, mutually exclusive mechanics of solar and lunar eclipse. What is notable for tonight's comparison is that a reddened sky, and specifically a reddening associated with the moon or with the general darkening of normal daylight conditions, is exactly the kind of visual signature that severe geomagnetic activity and the associated auroral displays can produce, particularly at the kind of mid-latitude locations where the Hebrew prophetic tradition was composed and transmitted. Auroral displays during severe geomagnetic storms are not confined to a thin green band on the horizon, the popular image most people carry of the Aurora Borealis. During the most extreme events, contemporary 19th century accounts, including those collected following the Carrington event discussed earlier in this report, describe the aurora taking on a deep blood-red coloration visible across the entire sky, bright enough to illuminate the ground and read by and visible at latitudes far closer to the equator than Aurora normally reaches. A red sky-wide aurora witnessed by an ancient observer with no framework for understanding its solar origin would very plausibly be described using exactly the kind of language Joel's text uses: darkness affecting the sun's normal function, and the moon, or the broader sky in the moon's vicinity, taking on the color of blood. This reading does not require treating the passage as a literal weather report rather than a work of religious prophecy, and we want to be precise about what we are and are not claiming here. The analytical observation is narrower and more careful than that. It is this: independent of what the author of Joel intended theologically, the specific visual description chosen, a darkened sun paired with a blood-colored sky, is structurally identical to the documented visual signature of an extreme geomagnetic storm's auroral display, a signature that would have been entirely unfamiliar and inexplicable to an observer in the ancient Near East, where aurora at visible, sky-wide intensity is a rare occurrence requiring a storm of Carrington-level severity or close to it. The language used is precise enough to be notable, regardless of what theological framework the original audience applied to the experience that may have inspired it. It is also worth noting, for completeness, that the Joel passage situates this celestial disturbance specifically as a herald, a sign preceding a larger event rather than the event itself, a structural framing that maps with a precision worth pausing onto the modern forecaster's own framework. A flare and an associated coronal mass ejection are themselves heralds, signals observed at the source that precede and predict a separate, later disturbance, the actual geomagnetic storm, arriving at Earth hours or days afterward. The text does not describe the sky darkening and the great and terrible day as the same moment. It describes the former as preceding and signaling the latter, the same temporal and causal structure SWPC's own forecast bulletins use when describing a flare observed at the sun as the herald of a CME's later arrival at Earth. A third tradition, originating in a region where the physical phenomenon this report has been tracking all evening would have been directly and repeatedly visible to ordinary observers rather than a rare anomaly, comes from medieval Scandinavia, preserved in the body of literature known collectively as the Eddas. The Norse sky, at the latitudes where these texts were composed and where the oral traditions behind them circulated for generations before being written down, regularly displayed the Aurora Borealis, and the Old Norse cosmological framework developed an extensive vocabulary and mythological structure specifically to account for what was, in that region, a recurring rather than exceptional sky phenomenon. The most directly relevant material comes from descriptions of Ragnarok, the prophesied end of the current cosmological cycle, found primarily in the Poetic Edda, a collection of anonymous Old Norse poems compiled in the 13th century from older oral material, and in the Prose Edda, compiled by the Icelandic scholar and chieftain Snorri Sturluson in the early 13th century as a more systematic prose account of the same mythological tradition. The Ragnarok narrative describes a sequence of escalating cosmic disturbances culminating in Surtur, a fire giant, advancing with a blade described as burning like the sun itself. An image scholars of Norse mythology, including those working from Sturluson's Prose Edda account in the section known as Gylfaginning, have connected to a broader Norse association between fire imagery and disturbance of the sky's normal order. Critically, the Ragnarok sequence, as described in both Eddic sources, is explicitly not a single, isolated event. The texts describe a sequence, a period of darkness and disorder, described using the term Fimbulvetur, the Great Winter, preceding the final confrontation, followed by Surtur's advance, followed by the sky itself splitting and the stars falling from their positions. Scholars studying the cosmological structure of this narrative have long noted its sequential, escalating character, multiple distinct phases building toward a culmination rather than a single climactic strike arriving without preamble. Norse oral tradition maintained by communities at far northern latitudes, where aurora activity is visible with some regularity even during ordinary geomagnetic conditions, developed specific vocabulary distinguishing between routine, low-intensity auroral displays and the kind of rare, sky-spanning, intensely colored displays associated with the most severe geomagnetic storms. Folklorists studying surviving Scandinavian oral tradition outside the formal Eddic corpus, material collected from rural communities well into the modern era before industrialization and light pollution altered the visible night sky, have documented a recurring association in this material between unusually intense, blood-red auroral displays and omens of conflict, upheaval, or significant coming events, a folk association that exists alongside, and likely predates in its oral form, the more literary Ragnarok narrative itself. What gives this tradition particular weight for tonight's comparison is the geographic logic underlying it. Unlike Babylon or the ancient Near East, where a sky-wide red aurora would have been a once-in-a-lifetime anomaly requiring an extreme storm to produce, Scandinavian observers at high latitude would have had the opportunity to observe the full range of auroral intensity regularly, from faint, low green bands during quiet geomagnetic conditions up through the rare, intense, blood-red, sky-spanning displays associated with the most severe storms. This means the Norse tradition's specific narrative choice to associate the most extreme version of that visible spectrum with cosmological catastrophe and the end of an age reflects not naive unfamiliarity with the phenomenon but the opposite. A sophisticated, experience-based gradation built from genuine, repeated observation that reserved its most dramatic mythological framing specifically for the rarest and most visually extreme end of a spectrum its observers were intimately familiar with across its full range. The people who recorded and transmitted this material, both in the formal literary Eddic compilations and in the broader oral folk tradition documented separately, understood themselves to be preserving an account of cosmic order, disorder, and the eventual unraveling and renewal of the world itself, framed through a mythological and religious lens entirely distinct from any modern scientific understanding. What they were not doing, by their own framework, was recording a weather report or an astronomical log in the deliberate, systematic sense the Babylonian scribes were. And yet the structural features embedded in their account, sequence rather than isolated event, an extreme version of a phenomenon their observers had genuine comparative experience with, and a narrative built around escalation rather than a single sudden strike, align closely with both the Babylonian omen tradition's emphasis on clustered recurrence and the actual documented physical behavior of severe geomagnetic storms, including the very storm sequence this report has been tracking since its opening section. A fourth tradition, drawn from a part of the world geographically and culturally as distant from Babylon, the ancient Near East, and medieval Scandinavia as it is possible to be, while still maintaining a documented, traceable oral record, comes from Maori cosmology in Aotearoa, New Zealand. Maori tradition maintains an extensive and carefully transmitted body of oral knowledge concerning the sky, the stars, and celestial phenomena, preserved through structured whakapapa, the genealogical and narrative recitation systems that Maori communities use to transmit precise knowledge across generations with a degree of fidelity that anthropologists, linguists studying oral transmission systems globally have repeatedly noted as remarkably accurate when checked against independently verifiable historical and astronomical events. Among the documented elements of this tradition relevant to tonight's report is the recorded Maori observation of and naming convention for the Aurora Australis, the Southern Hemisphere's counterpart to the Aurora Borealis, a phenomenon directly relevant given that NOAA's own forecast bulletins referenced earlier in this report specifically noted favorable aurora viewing prospects for the Southern Hemisphere's high latitudes during the current activity window. Maori tradition refers to the aurora using language connecting the phenomenon to Ruau Moko, a figure in Maori cosmology associated with earthquakes, volcanic activity, and the seasons. Born to Papatuanuku, the earth, and frequently associated in oral tradition with fire and disturbance reaching up from below the earth toward the sky. Scholars of Maori astronomical tradition, including researchers working with Maori community knowledge holders to document and formally record this material in recent decades, have noted that the association between aurora and Ruamoko reflects an interpretive framework treating the phenomenon as connected to deep, Earth-originating disturbance rather than as a purely atmospheric or distant event, an interpretation that, while built on a cosmological framework entirely distinct from modern geophysics, nonetheless reflects careful, repeated observation of a real phenomenon by a community positioned by latitude to witness genuine Aurora Australis activity with some regularity. This is also a useful point in tonight's report to formally answer the question posed at the start of the briefing section. 3 separate ancient traditions, the Babylonian Enuma, Anu, Enlil Omen tablets, the Hebrew Book of Joel, and the Norse Eddic tradition, described what is structurally the same underlying phenomenon, a reddened, disturbed sky associated with significant coming events, using entirely different languages, entirely different symbolic and religious frameworks, and calendars that did not share a common reference point. The Maori tradition discussed here adds a 4th, entirely independent line of observation from the opposite hemisphere. How did observers with no contact with one another, separated by thousands of miles and, in some cases, by more than 1,000 years, arrive at descriptions that converge this closely on the same physical signature? The answer this report offers is not mystical and does not require treating any of these traditions as supernatural prediction. The answer is observational. A sufficiently severe geomagnetic storm produces an aurora visible across a far wider range of latitudes than the phenomenon's normal, quiet condition range, frequently taking on a deep red coloration during the most extreme events. And any sufficiently attentive observer, anywhere on Earth, watching the sky carefully enough and for long enough across generations, would eventually witness this same physical signature and find some way to record it within whatever cosmological and religious framework their culture had already developed. The convergence is not evidence that any of these cultures possessed advanced knowledge of solar physics. It is evidence that the underlying physical phenomenon is real, rare, visually distinctive, and has been recurring in essentially the same form for as long as the Sun has been producing coronal mass ejections and Earth has had an atmosphere and a magnetic field capable of turning them into visible light. What gives tonight's specific forecast its connection to all 4 traditions, rather than to any single one, is the clustering. The Babylonian scribes specifically distinguished a single disturbance from a recurring one and weighted the latter as more significant. The Hebrew text frames a sky disturbance as a herald preceding a larger event rather than the event itself. The Norse tradition builds its entire cosmological narrative of catastrophe around escalating, sequential disturbance rather than a single sudden strike. And the structural fact at the center of tonight's report, established in the briefing section and never abandoned since, is that AR 44732 pending coronal mass ejections are scheduled to arrive within roughly 26 hours of each other, a clustered sequence rather than an isolated event, compounding a magnetosphere that has not fully recovered from the first disturbance before the second arrives. 4 traditions, 4 continents, 4 entirely separate religious and cosmological frameworks, and each one independently encodes the same basic insight the modern forecasting agencies cited throughout this report have built directly into their own operational models. Sequence and clustering change the picture in ways a single isolated event does not. What the people who recorded each of these 4 traditions understood themselves to be documenting was, in every case, something deeply embedded in their own framework of meaning, a sign from the gods, a herald of judgment, a feature of the unraveling and renewal of the cosmos, an earth god's disturbance reaching toward the sky. None of them understood themselves to be writing a space weather forecast. And yet the pattern is on the record in all 4 places, recorded independently, transmitted across centuries through entirely separate methods, oral and written, religious and observational, and arriving, when set side by side as they have been here, at a structural description that maps with genuine precision onto what the instruments above us are measuring tonight. The data is in the record, the interpretation belongs to you. As this report closes, here is the full picture we have walked through tonight. Sunspot region AR 4473 emerged on the visible solar disk roughly a week ago as an unremarkable patch of magnetic disturbance, and has, since then, grown into the single most closely watched active region on the Sun, producing an M2, 6 flare, an M6, 8 flare, and a flare in the M7 range, accompanied by a partial halo coronal mass ejection, all within a span of roughly 36 hours. NOAA's Space Weather Prediction Center has placed the probability of R1 to R2 radio blackouts at 40% for each of 3 consecutive days, June 22 through June 24, naming AR4473 directly as the source of that elevated risk, while the Australian Bureau of Meteorology's independent monitoring confirms the same region as the only one on the current solar disk showing meaningful magnetic instability. 2 coronal mass ejections, launched a day apart on June 19 and June 20, are now scheduled to arrive at Earth within roughly 26 hours of each other on June 23 and June 24, with KP index estimates for both ranging from 3 to 5, the upper end sitting precisely at the formal threshold for a minor geomagnetic storm. A separate, unrelated coronal hole stream is forecast to begin enhancing solar wind conditions in that same June 24 window, layering a third independent disturbance mechanism onto the most data-dense day of this entire monitoring period. We also covered in some detail the mechanics underneath all of this, how a sunspot's internal magnetic structure determines its flare potential, why a beta-gamma classification carries more weight than a simple beta region, how the KP index is actually derived from a global network of 13 magnetometer stations rather than arriving as a single direct measurement, and why genuine confidence in a coronal mass ejection's geomagnetic storm potential remains limited until the material itself reaches a solar wind monitoring spacecraft, positioned roughly 1 million miles from Earth. None of this is hidden information. It is published, public, and freely available from the agencies that produced it. What this report has tried to do is gather it into one place, in enough depth, to actually understand what is being forecast and why, rather than leaving it scattered across bulletins most people will never read in full. We walk through the historical instrument record, from Richard Carrington's direct telescopic observation of a solar flare in September 1859 and the telegraph chaos that followed, through the 1989 Hydro-Québec blackout that left 6 million people without power for 9 hours, to the 2022 loss of dozens of Starlink satellites to a comparatively modest storm, and found in all of them the same structural lesson: severity and consequence trace back not simply to a storm's raw intensity, but to sequence, clustering, and what happens to be vulnerable on the ground or in orbit at the precise moment a disturbance arrives. And we closed with 4 ancient traditions: Babylonian, Hebrew, Norse, and Maori, drawn from 4 separate continents and 4 entirely distinct religious and cosmological frameworks, each one independently encoding an awareness that a clustered, recurring sky disturbance carries different weight than an isolated one, centuries or millennia before any instrument existed capable of confirming why. Several specific things are worth watching in the hours and days ahead, and we want to name them directly rather than leaving this report on a vague note. First, the glancing blow coronal mass ejection arrival forecast near 8 UTC on June 23, the earlier of the 2 pending impacts, which SWPC's bulletin treats as the lower confidence, lower impact of the pair given its oblique trajectory. Viewers in regions with clear skies and minimal light pollution may want to watch for any Aurora response in the hours following that window, even at a modest level. Second, the more significant arrival forecast near 10 UTC on June 24, layered against the onset of the enhanced coronal hole solar wind stream during the same window, the single highest information point in the entire current forecast, and the one SWPC itself is treating with the closest attention. Third, AR4473's continued flare potential itself, which SWPC's 3-day outlook still places at a sustained 40% daily probability for R1 to R2 radio blackouts through June 24, separate from and in addition to the CME arrivals already discussed. Any escalation beyond the M-class range into a confirmed X-class event would represent a meaningful change to tonight's picture and would very likely prompt an updated bulletin from every agency referenced in this report. Fourth, the region's position on the solar disk, which remains close enough to the Sun-Earth line for roughly the next 4 to 5 days to retain meaningful potential for new Earth-directed activity, after which the Sun's rotation will carry AR4473 toward the western limb, and any further eruptions from this specific region will increasingly launch away from Earth entirely, a geometric clock running independently of however active the region itself remains. Fifth, the Aurora visibility window itself, with NOAA's models currently favoring high southern latitudes, including parts of southern New Zealand, as carrying some of the better prospects for a visible display this week. A detail Aurora watchers in the affected regions may want to track directly through SWAPC's own public Aurora forecast products rather than relying on second-hand reporting. Sixth, and more broadly, the underlying magnetic complexity of AR 4473, which has been increasing rather than decreasing as fresh magnetic flux continues to emerge from below the solar surface, a process that could in principle continue producing escalating flare activity for as long as it persists, or could begin to decay at any point, a genuine uncertainty every agency cited in this report has been honest about throughout, and one we will continue to track in future reports if the Region-S behavior warrants it. As this report is filed, the instruments tracking AR 4473 continue to update in real time, and the forecast windows named throughout tonight's briefing remain live and subject to revision as new data arrives, particularly once the pending coronal mass ejections reach the solar wind monitoring spacecraft positioned roughly 1 million miles from Earth, the point at which true confirmation of their magnetic orientation and density finally becomes possible. Tonight's sequence sits well below the severity of Carrington, well below the severity of the 1989 Quebec event, and the available data gives no agency reason to expect either to recur from this specific region in the coming days. What tonight's sequence does share with both of those historical events, and with the ancient record discussed in the final section of this report, is the basic structural shape, a disturbance that does not arrive alone, a second disturbance following close behind the first, and a planet whose response to that combination has, across the entire span of the historical and ancient record we have reviewed tonight, never been a simple sum of two separate, isolated parts. It is worth pausing, in this closing section, on just how unusual it is that this same structural insight, clustering changes the outcome, appears independently across every layer of evidence this report has assembled. NOAA's operational forecasters built it into their bulletin language without reference to history or myth, simply because the physics of magnetospheric recovery time demands it. The compiled record of 19th and 20th century geomagnetic storms shows it because researchers going back through telegraph logs and newspaper accounts noticed the same pattern recurring decade after decade, and four ancient traditions, with no access to any of that later evidence and no shared point of contact with one another, encoded the same basic distinction directly into their religious and cosmological frameworks, simply because their observers were patient enough and attentive enough across enough generations to notice that a sky which disturbs itself twice in close succession has always behaved differently and meant something different to the people watching it than a sky that disturbs itself once and then settles. We did not have to argue anyone into that conclusion tonight. The data argued it on its own, 4 separate times, across 4 separate methods of recording the world. There is also a quieter, more practical thread worth naming before we close. Tonight's report drew on data released publicly by NOAA, NASA, the Australian Bureau of Meteorology, the European Space Agency's joint missions, and a body of historical and academic scholarship spanning Assyriology, biblical textual criticism, Norse philology, and Maori oral tradition studies. None of that material is hidden or proprietary. Every claim in this report traces back to a source any viewer could, in principle, locate and verify independently, and that traceability matters as much as the conclusions themselves. A report that asks for trust in its authority without showing its sourcing is not the kind of report this channel exists to file. A report that shows exactly where every figure, every date, and every translated passage came from, one a viewer can check directly, is the only kind worth this hour of the night. We want to close with one final observation about scale, because it is easy, after an evening spent moving between satellite data and 4,000-year-old clay tablets, to lose track of just how small tonight's actual forecast really is in the broader context of what the sun is capable of producing. AR 4473 has not produced an X-class flare, The KP range forecast for its pending CME arrivals sits at the very threshold of a minor storm, not deep within it. Nothing in tonight's data points toward a Carrington scale event or anything close to it. What makes this report worth an evening of careful attention is not the size of the disturbance itself. It is the structure, a region growing in complexity in real time, a sequence of disturbances arriving close enough together to matter mechanically rather than as isolated points. A monitoring apparatus spanning continents, tracking it with genuine precision, and a 4,000-year human habit of noticing, in whatever language and whatever framework was available at the time, that this exact structural pattern, clustering, recurrence, disturbance, following disturbance, has always meant something worth recording carefully rather than dismissing as noise. What we filed tonight was a full accounting of a single active region, the agencies tracking it, the physics connecting a sunspot's internal structure to a forecast bulletin written in Boulder, Colorado, and the 4,000-year-old observational habit of noticing that the sky, when it disturbs itself twice in close succession, has always meant something different than when it disturbs itself once. That is the layer beneath tonight's headline that a quick scroll through a news aggregator would not give a casual reader, the cross-reference between what NOAA's bulletin actually says in full technical detail and what 4 ancient traditions, independently, recorded about this exact kind of clustered sky disturbance. We file a report like this every night on whatever the agencies are tracking that day, because the data does not stop arriving once most coverage moves on to the next headline, and the ancient record does not stop being relevant simply because it is older than anyone alive to read it. If tonight gave you something a faster take would have missed, tell us in the comments and let us know what this channel should look at next. Subscribing is how to make sure tomorrow's report is waiting when the data comes in. What happens next is on the record. We remain in observation.